look at some applications, but in contrast, so Nick was giving applications of an epidemiologist who's kind of trying to use these techniques and use them very nicely. Ricardo is going to present some of our work in Sheffield, which is from the other end, sort of people interested in the algorithms and the models who are stumbling around trying to apply them to epidemiology. And after that, we're going to move to James, who's going to talk us a bit about how you can try and get Gaussian processes working for very, very large data sets.
What do you mean try?
Well, we haven't done them on Malaria Atlas project. We can do it. Maybe they have to try to do it. And then we're going to have Hans Wackernagel, who we've heard a lot about, who's expert in the field of geostatistics, a PhD student of the founding father of the field. And then finally, we're going to hear from Simo Sarkar. And Simo's been working in an area known as state space models. And some of the ideas were starting to creep in at the end of Peter Diggle's talk, where he mentioned that you can use integrals to develop covariance functions. Well, those integrals can also be seen as the solution often to a differential equation, or when they can be related to state space models. And Simo's been working very much on temporal systems, but and efficient methods for very large temporal systems. And then the challenge there is introducing the spatial side. So instead of seeing the spatial temporal from the opposite direction, temporal spatial, if you will, which obviously should end up being the same thing. So that's quite exciting. Now, there was only one task for people to pass the Gaussian process winter school, and that was to pick up your certificate. So the following students have failed the Gaussian process winter school, and they are Pablo Strasser, Matsura Mokhtar, and Florin Christian Gavrila, and Marek Brabec. So they now have their last chance to claim that they passed the Gaussian process winter school. Otherwise, they've failed and the certificates will go in the bin. No one claiming 4 failures. That's not bad out of a class of 50. Better than my master's course, to be fair. And I think the exam was easier on the master's course. Okay. So without further ado, we'll pass over to Ricardo, who will tell us about illustrative applications.
Okay, so good afternoon. First of all, this is okay. It's not center. About this project is a joint collaboration between the University of Sheffield and Makerere University in Uganda, and main people involved. Of course, there's more people, but it's Neil Lawrence and myself in Sheffield, and in Uganda we have John Quinn and Martin Ronkisi, who's over there. He's actually visiting us for a couple of months, and so I don't remember how this collaboration started, but well, it's going well. So the people in Uganda, John, Ken Quinn, and Martin, have a very good relationship with people there in the Ministry of Health. So they did all this kind of problematic work that takes getting to the data. So they are providing us our data, and then it's expected for Martin in his project to make some predictions and construct some maps. Yeah, that's helpful. Yeah. So that's what they are expecting in that side, and we are helping by developing the model, the Gaussian process model. Now, all the work I'm doing, I'm coding it on GPy, as you would expect. But it's not only about saying, well, it's coded in GPy, but that's I'm mentioning this because that means that it's embedded in another kind of collaboration within the group, because it's not only my work, it's work that James has been doing, Alan has been doing, Nicolas, when he was here in the group, he was been doing. So I've been able to just take part of the work. When they build a kernel, I can use it. When they design some model, I can just rely on that model and build something on top of that. So that's I think that's a collaboration worth mentioning. So the data I have, it's a health management information system. They provide us with records from hospitals, the number of patients they get every week, I think. We have information from weather stations, like rain, temperature, humidity. We also have satellite information that Martin is processing and able to transform to give observations at different resolutions. We have geographic data, altitude and the location of the weather stations. And in the summer we went to a visit in Uganda, and there we were speaking to people in the health ministry, and they told us about this Sentinel data, which is similar to the data they provide in the health management information system. However, it's more accurate data, because the main data people is using, I don't want to say something that is harsh, but well, it can be misleading, because it's not actually tested that every person that is recorded has malaria. That there might be some errors in the Sentinel data. They only register those that have been tested and diagnostic, so which is more accurate to rely. However, we don't have information for the whole country on the Sentinel data, because there are some. They have just a few places where they are making the tests. So the features that we have in this problem is we have different spatial resolution from the data. As you can imagine, weather stations have some resolution. We have information from hospitals aggregated by district in Uganda, so that's quite a broad area. Temporal resolution is also different, because the frequency when we that we use for the satellite images is different from the frequency we get the records from hospitals. Information is really noisy. In some cases, it depends on the human error can be quite large. And our problem is that we have changes in districts and limits a long time. So that's really problematic, because we cannot build a proper time series for each district, because at some point they just split, or they just, I think they don't merge, right? They usually just split. So how to allocate the observations from one space, point in space to the next one, that's kind of difficult. So these are the places where they have weather stations in Uganda. And these are the places where they have the Sentinel sites. Those that have a round circle is the ones that we have the data now, and the ones that have a cross is data we are still waiting for. But hopefully we'll have it soon. And now I'm really glad people were making a lot of questions about the multi-output Gaussian processes we were speaking, because it made me feel that it's what I'm doing can be useful. So I decided to. Well, it's confusing. It doesn't matter. It allows me to speak here. So I will just go through it again in really fast, and then I will show the complication I have found trying to fit these models. So we have different tasks that we want to learn. For example, it could be the number of patients in each district. Each task will be a different district. And we have different inputs for each one, but we know there might be some correlation in those. So a way of solving it is just stacking all the observations in, like having just a single vector and doing the same with the inputs, and work it as a regression problem. Now the trick is how to construct the kernel. And then, so the kernel will have some shape like that one. So in this case, K would be a kernel function, and kernel function you would use in a regression problem. And the B matrix is the coregionalization matrix. So that matrix will be weighting every kernel for each block in the matrix, so that every output that is showing the kernel is weighting the same kernel in a different way. So a kernel can be more important for one output than for another one. If there are questions, just stop me. And then we can construct a general version of this kind of kernel by adding different B matrices multiplied by different kernels. So that can give us a good flexibility in the model. If we mix this kind of models with some MCMC, EP, or even Laplace, so we can put a different noise model for every single output. So in this case, this is just a example, and I place some log Gaussian noise in the first output, a Bernoulli noise in the second and third output, and there's the kind of result we will have. So we are finding some positive correlation between the first two outputs and negative correlation with the third one. Where you see the crosses is the observations we have for each output. So we don't know, in the third output, we don't know anything before 3 in the x-axis, but it doesn't matter because the model has been able to learn what's going on from the other two outputs. So that's the kind of work we're expecting from these processes. So where to start with malaria is it's transmitted by mosquitoes. So this is Alphonse Leveran, who's the first guy who was able to observe the parasites in human blood. So if the disease is transmitted by mosquitoes, we should look at weather data, temperature, rain, and things like mosquitoes like, and then from that we could move on. That sounds sensible, but it's not that the periodic pattern is not that clear. So I chose to show you what's going on in Arua, because it's well behaved basically. So periodicity is more clear in that one. So it's an example will look better. So this is the time series we have. This is the incidence, is the number of people that gets into a hospital and it's believed that they have malaria. It's scaled by 1,000. And so I can just go and fit a model, a single output model, and we would get something like that. And then I think here I'm just using an exponentiated quadratic or whatever it's named. But if we're expecting to see some periodicity, well, I could try some periodic kernel and I would get something like this. Now that's fine, but I don't know which model is better. Like I cannot tell, and I don't see a big difference between these two models. If I take some data out from the first model and plot it to see how it's behaving, I will just get something like this. And if I do that in the second model, it changes like that. So it's changed. I think in the change in the error bars is smoother in the second case when we are using the periodic kernel. In the case that if I fit a period, I cannot be really sure that this is the appropriate period for my model. So, and some intuition is, okay, the period must be correlated with the weather variables. So if I manage to correlate the rain, for example, in this case, with the incidence, and I can manage to learn the period from rain and share it with the data, then I might get a more sensible model. And that's what I get at the beginning. And then if I take some data out from the HMIS, it looks something like this. Still, I'm not sure if it's a very good model. So actually, in this presentation, I have more questions than answers. But okay, now how to fit this kind of kernels? And I will show this example with these three districts. The three districts are together, so they have a similar altitude. Well, they're not so different in altitude, and the weather should be similar in the area. So periodicity should be the same. Well, that's my intuition. Might be totally wrong. So first of all, I decided to include some bias, and the bias is helping to cope with the outputs with different magnitudes. otherwise I would need to standardize my data, because it's really tricky working with this kind of kernels. So if I just use a Bayes kernel, that's what I get. I just get the mean for each. My Gaussian process has as a prior 0 mean. So the mean is being learned just by the kernel, and that's what I'm getting. So what if I, on top of the bias, I add another kernel? Well, I have two choices. I can add it and use the same matrix B, the same matrix of coregionalization, or I can use a new matrix. So in the first case, I would get something like this, and in the second case, I get something like this, which seems to be more flexible.
Well, that's because the first model is a subset of the second one.
Sir?
The first model is a subset of the second one, so of course it's more flexible.
Yeah, good.
Is it any better?
I cannot tell you. I don't know if it's better.
We're still at the stage of trying stuff rather than claiming ground.
Yeah.
I mean, there's a problem with these models. As soon as you do that, so that wasn't low rank. Was that low rank or was that full rank?
Full rank.
That's full rank. So actually implicitly you have behind that, if it's full rank, you have as many latent processes driving this system as you have in the rank. So
yes.
if you want less flexibility, you can reduce the rank.
Yeah, but if I mean to put the question in a more constructive way, I mean, yes, your predictions are the result of a potentially infinite dimensional process, but the number of parameters in that model is modest, and you could use likelihood ratio as a basis for deciding whether the extra complexity is key.
Yeah, absolutely. Although it starts. This is one problem with these multi-output models. It starts getting less modest because it's quadratic in the number of output predictions you have.
Okay.
Or order quadratic.
Okay. In which case, you do have to know you've got enough data to have effective discrimination.
Bring up the previous slide. Previous again. I mean the one that looked different. Sort of thing. So if you make B low rank here, you can parameterize B with order number of output parameters, and then that can be a way of introducing this flexibility which allows, so let's say K1 and K2 are different length scale processes. K1 could be long length scale, but maybe that correlates across the outputs in a different way to the way that K2, which could be short length scale, correlates. So you want both K1 and K2, but implicitly if you've used full rank, you've got DK1s and DK2s, which is perhaps too much flexibility.
Yeah. But I mean, you've got a structure there which is kind of nice because it's implicitly nested, and therefore you can build incrementally and have some measure of how much you're gaining in predictive power with each incremental complication, rather than just relying on pictures.
Yeah, absolutely. So I think the reason we're relying on pictures at the moment is because we're still we don't have conclusions yet. We're just trying to sort of show what the different types of things we could do.
Sure. Nice.
So, that's the difference between the intrinsic model and the linear model. Now, the next question is, do we want correlated components in the kernels, or do we want uncorrelated components? If the components are correlated, it's like in the first case, the matrix above, and if they are uncorrelated, then we just have the big kernel matrix has just elements in the diagonal blocks, and it's zero everywhere else. And these will be like uncorrelated components, and the correlated components are the first case we showed, which of course can be more flexible. Now the thing with the uncorrelated components is, if you are working with the same kernel matrix K, we might have some independence between the outputs. However, the parameters of the kernel are still shared. So if we are using any parameter with some length scale, the length scale will be the same for all the outputs. So we might want to add some parameters with different length scales for each output, which would be something like this: a different K for each in each block. And well, it's not a big change, but if you see in the second plot, just before 2005, the model is clearly has a shorter length scale than in the first case, where the drop in the incidence is smoother. And then, well, if I have a periodic kernel, because in all these cases I'm just using some bias and the exponentiating and quadratic. If I add on top of that a periodic kernel, and I'm assuming that the period is similar for all the outputs, so that in that one is being shared across all of them. That's what I get. Now, okay, the next question is, I'm adding a bias, I'm adding some other kernel and a periodic kernel on top of that.
Can you just remind us what each, because we can't see the axes on the left, what's the top, middle and bottom?
Okay, the top one is Aruba. The
next three regions?
Yeah, the different districts. And then, okay, we have different kernels. And what I have observed is that these kernels, one kernel is dominating all the others. So the periodic component, when I add them, the three of them, is just taking account of almost all the variability in the model. So the RBF seems to be redundant, which I'm not sure if it's because of well, the maths make it being redundant, or if it's just computationally redundant, because we are optimizing the likelihood to define the parameters of the model. Now, the biggest change is clearly in the periodic kernel, and in the others, is it? I don't know if it's because of precision in the model, in the computer, or whatever. The point is, I could just get rid of the RBF in this case.
I think that goes back to Peter's point. Actually, you can test for that. You can easily test between the two models, the periodic model or the standard RBF model in two different models, and then compare the likelihoods you get with each, and just do a standard likelihood ratio test, and then you actually have a statistical validation for whether the signal's dominant periodic or more RBF. And the suggestion is, because it tends to be favouring the periodic, I would guess it's more likely to come out in favour of the. But you would be able to quantify it better.
And that would be an interesting thing to do, with exactly these data.
Yeah.
See how much your judgment by eye is actually picked up as an objective change in the lining.
Yeah. Okay, so well, it might not be clear, but here what I'm plotting is just the B matrix of image. And so, and then I will give you will share some of the ideas I had to run the period, because before I was just using the data like that. But if I want to learn the period from a weather variable, maybe in my model I'm not interested in learning all the variability of the weather variable. Maybe I'm just interested in the period. So I was thinking that maybe it would be useful to work with binary data, for example. So to tell you when the variable is below its mean and when it's above its mean. So the first thing I did was just to make it binary, both outputs, the incidence and the temperature. And I just fit a model, and so I can correlate to binary outputs, and the result is like that. But okay, for incidence, I'm interested in all the variability, so I can just correlate and work with a binary variable in the weather, and work with the actual values in the number of patients, and that's what I get.
So the idea there is that if it's loosely correlated, if there's some threshold in temperature above and below which the mosquitoes are active, then this is a better way of, I guess, sharing information across the outputs, because the actual value of the latent function is less important than the observation that things have gone above a particular temperature.
A lot of this is about language, technical language, because the statistical version of what you've just done would be to say we've got this continuous variable, and if we just correlate it with the number of patients, we're assuming linearity.
Yeah.
If instead we break it down into a bunch of factors and fit it as a factors, we could then look at the factor parameters and see if it was approximately linear or not. And what you're saying is one possibility is that actually it's a step function. And then as you increase the number of levels in that factor, again it's about complexity has to earn its keep. you might find that actually a step function fits perfectly, or you might find that if you then broke down those steps into sub-steps, things got better. But the value of doing this would be if and only if it's not linear to start with. Because if it's linear to start with, there's no point throwing away the data.
Yeah. Although, actually, that's interesting. I would say this is less complex than linear. Because there's less...
I'm sorry, again, it's about language. To a statistician, well, to this statistician, complexity is how many unknown parameters you're estimating. And if you've got a binary regression, that's one parameter. If you've got a linear, that's one parameter. So they're equally complicated.
Right, yeah.
Yeah. But if you break it up into lots of factors, that's complicated because you're using a lot of parameters to describe what might be a nice smooth function.
So because with threshold, I'd say there's one parameter, and then linear there's two, because there's an offset and a scale.
Well, I think you have to have two either way, because you've got to have a value for 0 and a value for 1. If you're relating it to something else. Anyway, that's kind of rather obtuse. But it's interesting because it's just a different way of attacking a similar question.
And well, what it's next in this research is just to be sure what's happening with that dominance between the components of the kernels, and to find out how to work with the parameters redundancy. Because we might just be making our models to run slower than needed if we just throw a lot of kernels and let the model run everything. There must be a way of going around that. So far I have just spoken about the temporal dimension. We still need to embed the spatial dimension. Well, we have to extend the model to the whole country, and that will bring some new problems, and part of those problems are problems that James here is going to speak about when the data just becomes really large. And thank you.
I mean, just on some connections I see with some of the things Peter was saying, when you say spatially extending to the whole country, these are in departments, and so you would be looking at potentially a Markov random field model here. So one thing you can take, that matrix B was actually dealing with the correlation between compartments. Now the interesting thing, I'm saying that could be low rank, right? So there's two ways of taking a matrix B and reducing the number of parameters. Two ways, there's many ways, I'm sure. But in my mind, if you're not going to parameterize it functionally in some way, there are two obvious ways. One is to make it low rank, and the other is to make it sparse. Now, if you were to say that use this structure that Peter was talking about, the inverse of that matrix B would be the connectivity of the Markov random field. So in that case, you're making its sparse inverse. And I think that those are two very powerful ways of dealing with this co-regionalization matrix. That you can either say low rank, that means you think there's a reduced number of processes being mapped out to do lots of things, or you can say it's sparse inverse, and that means you think you've got some sort of spatial structure, or it could be typically spatial structure, where you're only affected by your neighbours. And that sort of ties it back in. When you see these departments, that's one way of making the matrix B reflect that department structure across the country.
And the geography there is quite nice, in the sense that it's compact regions of same order of magnitude, roughly the size. So the neighbourhood, the nearest neighbour rule, although in a sense it's arbitrary, is not unnatural in that sense.
Questions? James, you want to start setting up while we get questions? Just so that
more of a general maybe do these co-regionalisation type approaches have any relation to the Gaussian process regression network
I'll have to remember those. There's two different algorithms were invented and called Gaussian process regression networks. That's point one. And I think we're talking about Andrew Wilson's one.
Yeah.
And I've read the paper, but I can't remember what it involves.
The Gaussian process regression.
I don't know why I'm putting it on. It was. How does it relate? The question was, does it relate to the Andrew and Zubin's Gaussian process regression network?
So imagine just have co-regionalized Gaussian processes over one variable, and then you have a Gaussian process prior over the co-regionalization matrix over the other variable.
Yes, thank you. Yes, it's sort of products of yes. So you put that on.
That's cool on that.
So in that case, what they do is they make the B matrix stochastic. And if you make the B matrix stochastic, you've blown it all apart in terms of tractability, but you get this sort of Wishart type process effect. And you do get a lot of flexibility out of it. It would be sort of like saying, in fact, the original motivation in Hagen's paper for Gaussian processes was some kind of weights in a linear regression shifting over a spatial field. If you look at the original paper, he said, I want to do linear regression over beta, but I think beta changes according to some input, and he made a sort of Gaussian process prior over beta. That's kind of like doing that same idea again, allowing this matrix to now vary over this field, and it leads to these sort of multivariate Wishart processes, but then it also leads to some lack of tractability, but quite a powerful approach. Yeah, and that's right. Yeah, you talked about it here, and in fact, what you can get, and Zubin's shown these results reanalyzing the Swiss Jura data that's famously geostats, where they show spatially how those Q regionalization matrices vary across an entire domain. There's a risk of adding, if you add that extra complexity without treating it stochastically, in a sort of Bayesian treatment, there's a massive risk of overfitting. So the reason you want to do that